So everything you do online, every purchase, every message you send, it's all protected by this invisible shield, right? Cryptography. Well, in 2024, that shield got some serious dents. Actually, it didn't just bend. It flat out broke in some places, causing these massive, massive failures. And if you think that's bad, what's coming next with quantum computing? Well, that could shatter the whole thing for good. And I'm not talking about some minor glitches here. Nope. 2024 was a year of, well, catastrophic security failures. The impact wasn't just some numbers on a screen. It was real world. We're talking hundreds of millions of people, thousands of businesses. The ripple effects touched pretty much every part of our lives. So you gotta be asking, what on earth went wrong? To really get a feel for the kind of pressure our digital world is under, we're gonna look at two huge events from that year. They're totally different on the surface, but when you put them together, man, they show some seriously scary cracks in our defenses. Okay, first up, the huge CrowdStrike outage. Now, you might think this was some super sophisticated hack, right? Nope, it was a tiny, and I mean tiny, human error. A software update had a simple mismatch. Think of it like a plug with 21 prongs trying to fit into a socket that only has 20 holes. It just doesn't work. But because this software runs deep inside the operating system at the very core, that one little mistake triggered the dreaded blue screen of death for businesses everywhere. We're talking grounded flights, stalled financial systems, total chaos from one tiny slip-up. And then there was the Snowflake breach, a completely different kind of disaster, but just as bad. The way the attackers got in was, well, it was almost ridiculously simple. They went on the dark web, bought a bunch of stolen usernames and passwords, and then just tried them. They were looking for accounts that didn't have multi-factor authentication turned on. And once they found them, they basically had the keys to the front door and just walked right in. So what was the price for not turning on that one extra layer of security? Well, the attack hit at least 165 different organizations, and the data of an estimated 30 million customers was stolen. 30 million people. That is the kind of insane damage that happens when you ignore the absolute basics. And this quote, man, it just nails it. The scariest part about these huge breaches isn't that hackers use some crazy new futuristic weapon. No, these were failures of the most basic stuff, the fundamentals. These are the same old weaknesses that keep biting us over and over again. So, this means we've got to go back to basics. Doesn't matter if it's a tiny coding error or a simple stolen password. Both of these disasters show what happens when we forget the fundamentals. So, to even begin to prevent this stuff, we really need to understand the two core rules that our entire digital security world is built on. Let's break them down. Okay, rule number one is data integrity. The easiest way to think about this is like a tamper-proof seal on an envelope. You know, the kind that shows if someone's tried to open it. It's the absolute promise that the message you just got is the exact same one that was sent. Nothing added, nothing taken away, nothing changed. At all. All right, and rule number two is origin authentication. So if integrity is that tamper-proof seal, authentication is how you know who actually put the seal on the envelope in the first place. It's the guarantee that the message isn't a fake, and it really truly came from who it says it came from. No imposters allowed. Okay, so we've got our two golden rules, data integrity and origin authentication. But how do we actually enforce them? How do we make sure they're followed? Well, that's where the basic tools of cryptography come into play. Our first tool is something called hashing. Imagine taking any piece of data, a picture, a document, anything, and shoving it into a special kind of mathematical blender that only works one way. What comes out the other side is a unique fixed-length code. We call it a digital fingerprint. And here's the magic part. If you change even one tiny little bit of the original data, the fingerprint that comes out is completely different. It's how we guarantee data integrity. So hashing gives us that perfect tamper-proof seal. Great. But wait a second, that leads to a pretty important question, right? How do you know the fingerprint itself is real? How do you know it wasn't just faked by someone else? How do you trust the sender? And the solution is it's brilliant. It's called an HMAC. What you do is you take that digital fingerprint, the hash, and you mix it with a secret key, like a password, that only the sender and the receiver know. It's kind of like sealing your message with a secret handshake. And just like that, bam, you've got both data integrity and you know exactly who sent it. Problem solved. Now, this whole idea of keys brings us to encryption, and there are really two main ways to do it. First, you've got symmetric encryption. That's where you use one single shared key to both lock and unlock your data. It's super fast, but you have the problem of sharing that secret key without anyone else seeing it. Then you have asymmetric encryption. This is the clever one. It uses two keys, a public key that anyone can use to lock data and send it to you, and a private key that only you have to unlock it. It's a bit slower, but this is pretty much the foundation for all secure stuff we do on the internet. Okay, so we have this amazing toolkit, right? Hashing, encryption. When we use them correctly, they keep our digital world safe. But here's the big plot twist. What happens when all of these amazing tools have an expiration date stamped on them? And that brings us to the final, and honestly, the most critical point of this whole conversation. We need to be agile. Because this isn't just about fixing the mistakes we already made. We are staring down the barrel of a huge crisis in trying to future-proof our entire digital existence. I mean, just look at how we've handled this in the past. Back in 1977, the gold standard for encryption was something called DES. But we figured out pretty fast it wasn't strong enough. So we came up with a temporary fix. The real replacement, AES, was ready to go in 2001. But guess when we finally got rid of that temporary fix? 2024. That's a 23-year transition. To say we're slow at this is, yeah, that's a massive understatement. This is exactly why we so desperately need what the experts call crypto agility. So what is that? It's basically the ability to swap out old, broken security tools for new, stronger ones, without breaking everything in the process. The best analogy, it's like trying to change the tires on a car while it's still doing 70 miles per hour down the highway. It's tricky, but we have to be able to do it. So why is this suddenly so urgent? Well, the number one reason is the huge threat of quantum computers. These are machines that will be powerful enough to just shatter a lot of the encryption we rely on today. And we already know from our history that it takes us decades to upgrade, which leaves this huge window where we're totally vulnerable. Plus, upgrading is super complex, it's expensive, it messes everything up. We have no choice. We have to get faster at this. And that leaves us with one final and pretty urgent question. Our entire digital world, everything we've built, it all rests on this foundation of cryptography. The messes of 2024 showed us that the foundation already has cracks in it, just from simple human mistakes. But there's a much, much bigger earthquake on the way, and it's called quantum computing. So the real question we have to ask ourselves is, can we get agile enough to fix that foundation before the whole thing comes crashing down?